Hello, good afternoon. We are here. We're about to finish chapter 5 of Essentials of Compilation. I'm pretty excited. This chapter was challenging. Um, this entire book is challenging. But this chapter has been challenging especially because we went from the very straightforward, hierarchical, lexically scoped, immutable sort of control flow to loops. And loops, in order to work, require mutability, and they require circular kinds of logic of thinking. And so I think we've accomplished a lot, and we're very close to finishing the chapter. We started last time finishing up the starting the liveness analysis, and breaking apart this algorithm that they have in the book, for doing the data flow analysis and building up the liveness of variables and registers with a fixed point algorithm. So using lattices, namely here the grow only sets, for computing those liveness calculations. So we're very close. Last time we got the outline of the algorithm. What we didn't get were the function that computes. It goes through the algorithm that we did first in chapter 3, computing the live before sets from the live after sets by walking backward through the set of instructions. So we have very little to do. We just have to refactor some code and write some tests, and we can call chapter 5 done. I think we will want to make sure that all the rest of our phases that follow the liveness analysis, that they still function correctly. So we're going to have to do some steps where we go through the rest of the tests, ensure they are still correct, add some new tests that cover additional functionality, maybe modernize some of the tests that we have now that we have a Lexern parser, and we can just build up an example program from something that's more understandable, and then we can call chapter 5 done. So I don't know if we finish it today. I don't know if we'll go on to chapter 6. We took a break after chapter 4, which I think was really good, and I might want to do another break after chapter 5. So we have some interesting opportunities there. There are a few possibilities. One that I've mentioned multiple times on this stream is that we might go and build like a compiler explorer type of website thing. That'll be interesting because it'll get us into more Gleam FFI. We'll introduce FFI to JavaScript, since that is a target potential. And we will also possibly look at another wonderful library from Haley, which is Luster, which is an Elm style user interface library. So those are possibilities that we could go with. There's also some challenges that were earlier in the book that we did not complete. One that's sticking out in my mind is that there are some cases where we are generating, on conditional branches, we are generating blocks that never get entered. And so we might do the challenge, go back and do the challenge where they do dead code analysis, essentially. That that branch will never be taken, therefore we can eliminate that block, and that'll give us smaller programs. But those are some possibilities. Just as a preview, if you haven't looked at the book before, chapter 6 is tuples and garbage collection. So when they say tuples in this context, they mean vectors. I'm guessing it's fixed size collections. And of course, garbage collection is an essential part of something like that looks like Racket. It has scheme-like semantics in that respect. So garbage collection is essential for this kind of language. Now, we could also, when this whole journey is over, and I don't know if we'll get through the entire book. It is 11 chapters, and so that means we're approaching halfway through. But there are other possibilities we could do after we're done with this book. We could design our own language and do the same sort of effort of building multiple passes and compiling through those passes multiple intermediate languages. That might be kind of fun. I don't know what kind of language I would want to do yet, but it is something I've been thinking about. So let's get to it. If you want to follow along, remember the GitHub repo where we have this is Sean Cribb's Essentials of Compilation. And we are, again, building this in the Gleam language. So we will have lots of fun, I hope. All right, so again, we were in chapter 5. We were looking at section 5.8. You can see this is the end of the chapter. There's a lot of white space down here. And where we were was we had, now my editor is complaining because these are all unused. We'll wire it up at the end. But we had just completed this analyze data flow. And because Gleam doesn't have loops in the same sense that, something like Racket has loops. I meant to get the book up. There we go. If we go up here and we look at their analyze data flow, where was it? Did I just miss it? Section 5.2. Okay. Is at the end of 5.2. Yeah, this is the whole explanation of building up sets and computing a fixed point and so forth. Okay, here we go. So theirs makes use of the while loop that's in Racket. We don't have a while loop in Gleam, so what we do is we create a function which sets up the initial state of the loop, which is essentially this stuff that comes before it. So we make a mapping, and then we call this. And I actually want to, let's rename this symbol from flow inner to loop. That makes a bit more sense. Okay, so we are taking our control flow graph, and I think I want to make some type aliases for these things at some point, because this type signature is getting pretty brutal. So their loop is looping over a work list. So the work list is basically, it starts as all of the vertices in the control flow graph, which are all the blocks. And then it takes a node off the work list and then figures out what its neighbors are. This is, so here we took a node off the work list. I'm doing it with pattern matching, but Over the last week, I did discover there's a deck library that we could pull in if we want. I don't think it's really necessary for this. We're not going for efficiency. We just use list append. Again, not the most efficient thing, but we haven't hit the need for efficiency yet. Okay, so we're taking a node off of the work list, and then we find all of the live before sets for its neighbors. So the things that it can jump to, potentially, the other blocks that it can jump to. And that's making the set union over those. So that's what this is doing. It's saying, get me the, excuse me, get me the mapping for the for this neighbor, the inbound neighbors. So remember, our graph is already transposed. That's the way we built it. Was that we go from the destination to the spot of the jump rather than the other direction, which is the more natural way, and then we don't bother worrying about transposing. I'm guessing that, and I may have mentioned this last time, I'm guessing in Racket that there aren't outbound neighbors, so it's not, you can't look at edges going the opposite direction. But the digraph module in Erlang, which we're using in our FFI, it has both in and out neighbors, and they're pretty efficient. It's just ets tables with pattern matching. I'm sorry, like the built-in like VM matching is it's stronger than regular pattern matching. Anyway, so we're getting the inbound neighbors for this node, and then we're building up from an empty set. Right, so it takes bottom, and it's join the input set with the before the live before set of that particular block that's being jumped to. Okay, and then it says assign the variable output, call this transfer function with the node, which is like whatever the block name is, and the input. Now, specifically, what they're doing is this transfer function is supposed to be passed into this, with higher, like as a higher order function. So this can be generic. We don't need that yet, and also I don't know if that's a really good idea for the kind of thing that we're doing. But essentially, they're saying, oh, we'll just give the the set and the name of the block, but we pull out the name of the block, or we pull out the actual code of the block here and pass it into this function. Okay, and then we're getting whatever the live before set was for this node the last time. If they're equal, then we just continue through our work list. If they are not equal, then we replace it and we append all of its neighbors. So basically, the things that jump to it, we put them on the end of the list. So this is that fixed point thing. We know that if this one changed, then the things that pull from it for their live after sets probably changed. So we need to make sure that we visit them again. And this is this kind of iterative working toward the place where there's no changes. Okay. So we need to implement this transfer function, and we did that before, and I'm gonna get that back out to the full width. We did that before in this compute live after. But really, what it needs, we only actually care about the live before of the first instruction of the block, right? So I think we're going to copy paste this, and we're going to modify. Okay. So instead of there's a lot of. So we're going to say we're going to fold right over instructions, and the input is going to be the live after set, right? So I'm going to call this live. And this is going to be the live set at the current instruction. So, or the instruction basically after this one, right? So we don't need to pull it off of the list. We have that set. Okay. So this, we're going to, let's rename this symbol to live. And we're going to have to fix this stuff. So basically, if it's a jump that to conclusion, it doesn't change anything. And the other interesting thing is if it's a jump to any other label, we don't need to get that because we fed it into here. So as an input to this algorithm. So honestly, if I think what we do here, this actually gets really simple, doesn't it? Because we don't have to handle jumps explicitly. And on any other, because we've already have that input, and on any other instruction, we were just leaving it unchanged. So this becomes before set. Oh, I love it when a plan comes together. Okay, so now it's just complaining it's not used. So our transfer function is really fold right over the instructions given the input set and compute the before set. Duh. Oh, that's nice. Okay. It's what we did was in our last pass at doing this liveness analysis, we made these little functions like the before set, which looks at the after set and the instruction and finds the right locations in the instruction and the read locations in the instruction and does their little set analysis. So that's pretty awesome. And I don't think that we need to, there's nothing missing here. We didn't change the target language of this pass, right? So now what we're going to do is instead of this, went faster than I thought. I'm really pleased. Okay, so we're going to compute what the new blocks are. And really that amounts to we need to call this build CFG, right? This, I guess it's body, right? Okay, so this is build CFG. Let's make a pipeline. And we have to pass the input body again, right? So, no. We build the CFG, and then we pass that to analyze data flow. Here's where we pass the body again, right? Because the code here is unmodified. So this is going to return the block to the set of locations. So this is the before, the live before set. So then we will do let's do dict map values. That's good. And this is going to take the key and the live before. And let's do... The interesting thing is we don't need this live after, so we may go and remove that from the block structure. So this is the block and the live before. Okay, so what we need to make sure to do here is fetch let's say block name. Right? Okay, and then that's just saying it's not used. That's a string. Oh, it's just saying we're return. Wait, what? Okay. So now we can say block live before. What is wrong there? Oh, I need to switch this. Oops. The dictionary comes first. Okay. So really we're just getting the block out of the input and updating its live before set. And that's all this phase has to do. And I don't think that, let's pop our Project Explorer back up here. I don't think that allocate registers uses live after. Right? Really all we've done is updated the way that we compute the live before sets. And oh, here's the problem. We do need this to be a list. Unfortunately. Because we use the live after part to allocate registers or build interference. Yeah, so we use that to determine conflicts. So I do need to get I do still need to build that live after. So we are not quite done. What we're going to do here is we're going to have to we're going to do that, and because I think that what we did before, let's look at what was before. Right, that's exactly what we did. So we are going to update our transfer function. So we can't do just this. I feel like there's a full map thing that we might be able to use. Let's look it up. Let's see, packages. Or do I have it out here? Yeah, there we go. Standard lib. Okay, we got the latest. Gleam list. There's fold right. Their map fold. I think the problem with map fold is that it will always go left to right, and we need to go right to left. All right, well, what we'll do is we'll do, yeah, I think we need to do something that's more like this. So rather than have this, you know, sets from list, RAX, RSP, etc. Although I do think we need to inject that. We'll see. Yeah, let's do. We're going to put this into a list, and this is going to be a list of sets of locations. This is going to make our algorithm a little bit more complicated. I'm going to flatten this. So what we want to do is we actually want to do I think I did list first. Yeah. And then we do before set of that takes the previous, or let's call it next, because it really is the next instruction, and then we'll take the instruction and then we add the live after. Okay, so the problem here is that now we can still do output equals previous. The problem now is that our mapping has to be a list. Oh, this is going to be messy. it has to be a list of sets, and I think that this is where I don't like this, but we're going to do set like we did in the other one. We'll do set from list and just assume that we are, yeah, this is exactly what we want. And I've broken everything. Woo! It's this. Okay. So the problem here is this gets us we need to redo this. So I think it's okay if we're checking that the list of sets is equal to the previous list of sets. That's fine. The problem is our input needs to be a single set. So what we need is I'm gonna let assert. I'm kind of we construct we construct the whole set, like every single block gets the base thing, right? So we don't need to lazy unwrap here. So I'm gonna do another thing, and I'm gonna do that, and I'm going to say okay. Okay, now the problem is we need this. We need to update the type signature of the return. And we need to update it here. Okay, this is where, like, if I had made type aliases, a bunch of things would be easier. So let's go ahead and do that. We're going to say type mapping is this. We're going to say type blocks is this. And we're going to say type CFG is this. Okay, and then we'll fix all this stuff. This is CFG. This is blocks. This is mapping. And let's go ahead and make one for work list. Okay. And we'll change this to work list. Okay, and this is mapping. Cleaned a lot of stuff up there. Transfer. Why don't we make another type? Live set. And then we can say this is a list of live set. that's a little bit better. Here's a live set. And this is a list of live set. I'm just trying to add a little clarity here because this stuff is getting, yeah, that function is no longer used. So, because we don't use the topological sort. And this, again, here we can go, this is blocks, and I'm returning a CFG. And we're no longer using this. So, this takes a live set and computes another live set. And this computes a live set. And this computes a live set as well. Okay. I think that adds some clarity. We could write some documentation for these things. But at the very least, our type signatures are a lot less verbose on our functions. I think it's going to reformat this, but I just want to see if it'll go on one line. Yep. Okay, never mind. Okay. So, this kind of makes me wish there were like a dictionary zip type thing, or let's see if what else is available in the dictionary module. Yeah, I don't know that that helps at all. Because we still have to combine it with the mapping. Okay. So we need to look at our test, make sure we didn't leave anything out. Make sure it compiles. Okay, so we have warnings about unused modules. That's fine. Let's run the tests. Woo, that's fun. Undef. Where does that come from? An unexpected error occurred. Undef. And it's not reporting what test failed. It's possible we have some let asserts in places that are bad, but let's do one thing I want to do is Gleam 1.12 is out, so we're gonna upgrade Gleam. I should have done this before the stream, unfortunately, but here we are. And you're going to install all that business as well. Because I suspect there's something here that we're doing in that test. That's weird. Already linked, whatever. Okay, well, let's relink. Okay. So I think that there's probably something in here. or there's some let assert in here that's failing. Right? I don't know what that undef was, but did I not just update Gleam? Or was it that WX widgets that failed? Okay, now it says 1.12. So I need to update. Yeah, so we need to get a new version of Gleam Erlang. And I think standard lib, it says v062, so I think that that's fine. That's what it got. And Glee unit. Okay, so let's see what the Gleam command can do. Okay, so that let us force upgrade. Yeah, okay, so like the add command is putting in its own constraints there. Let's see if there's anything. Okay, so let's build again. Okay, so we have a problem here. It's no longer called Gleam Erlang. What is it called? Maybe this get line. Yeah. All right. Well, let's look at This may no longer do what we want, but we can look at now port, process. That's not going to help. Application. Yeah, I think probably what we need to do is instead of this, we will do, and let's look back at the Gleam standard lib, because this is Gleam IO. Okay, so this is just for printing. So we need to do our own get line. That doesn't use Gleam Erlang. And that's interesting because I think that means, and let's just look. Okay, we've got it in a lot of places, but none of these are. Yeah, we just need to make our own FFI module. So let's go in here and see Erlang.getLine. Okay, honestly, I think what we do is we put this, because this is for the interpreter, right? we put this into an Erlang FFI module. Yep, let's just make a, let's see. Yeah, so the pattern I was doing was, let's make a new file called runtime.gleam here. And then we will make a new file in here, which is runtimeffi.url. Okay. And this is going to export read int 0. Okay. And then we'll do basically what we were doing in this, I'm sorry, this other place. So runtime.gleam is going to say read int. And I think it was, yeah, it just returns an int. So it's going to have to swallow any errors that it encounters. And this is, how do we do that here? Yeah, so we do external Erlang, something like that. And this is going to be runtime FFI read int. Okay, so then we will pull this down, and we'll use getLine in Erlang. Yep. Okay, so we will do getLine. Let's look at the Erlang docs real quick. I think it's actually IO. It's IO getLine. Yep. Okay, and that returns either a data or error. Okay. Okay, and get like the prompt. Sorry, you all can't see that. I'm sorry. Okay, so you give it a prompt is an Atom or Unicode char data. So an Erlang string is fine. That's a list of code points. Okay, so if we get so this server node data, when what the IO server sends when there's no data, is either an error tuple or EOF. We're going to exit EOF. And then the other option is error. We'll exit error. This is not great, but okay, so if there's data, then we need to do Erlang list to integer. Is there a binary to integer? Binary to integer. There's a question in my mind about let's look at io_getLine again, because I think that data is a string or a Unicode binary, so we need to do binary binary to integer of io list to binary data. And then what we'll do here is instead of this, let's find where this is used. Final references, please. Okay, that doesn't work. So let's go up here. Read int. Okay. So what we'll do here is we will, rather than Gleam Erlang, we'll import runtime. Is that EOC runtime? And then where did that go? Say runtime dot readInt, and then we can get rid of this function. And honestly, let's find all the places that do that. We found it a minute ago, right? And a lot of this is just copy pasta, right? So readInt. Okay, so let's do import EOC runtime. Okay, and then say runtime.readInt, and then let's find the other place where it is, and we get rid of that. Basically, we need to do that to all of these. Now, like, these intermediate languages are no longer valid. They're just leftovers of our process, so maybe we don't need to keep them. But I want to fix all of those. Oh, interesting. We're not using those either anymore. Cool. Okay, so that, I think that's going to mean that we don't need these other ones either. But let's find readInt again. Oh, I'm sorry. Top of file, import EOC runtime. Okay, so this is runtime readInt, and then we can get rid of this function. And now we don't need any of those. Woo! Nice. Okay, and I'm guessing that what's going to happen is we can get rid of that and readInt. Oops, we need import EOC runtime. Ultimately, this, we're calling this in our interpreter for these high-level languages, but the implementation for x86 is their runtime library that we would link to that's available on the compiler's course GitHub account. Okay, and then yeah, so this is our last one. readInt. Yep. Okay, so that's the only place it's called. So we just need to remove the unused imports. Okay, so let's find Gleam Erlang. We're not using it. I think this is actually good that they have kind of cut down the surface of that library, and now we don't even have to have it in our dependencies. Now that does mean we have to maintain our own FFI thing here, but it makes sense that they don't put that in the standard lib, because depending on what your target is, you may not have a prompt to read from, right? So it doesn't make sense to have that in there. And now what's wrong in here? Oh yeah, we didn't get rid of this function. So, oh, and that was our partial evaluation. That's another challenge we could go through, is do some partial evaluation in our bubble up constants and that sort of thing. Constant folding, I think that's the word for it. Okay, so in this whole big journey that we just did, our goal is to be able to run the tests and not get undef. So now it's actually telling us what tests failed. I'm not sure what this undef is, so let's see if we can get the LSP to find it. So let's look at allocate registers test. No, the tests, please. Okay, let's look here and see if the this is gonna be frustrating if I can't I can't find why it's happening. So it's happening in uncover lib, build interference, and allocate registers. So build interference immediately follows uncover live. Let's look for what this undef means. I'm guessing we're calling something that does, like a function that doesn't exist, and that's what the undef is, which would be frustrating. I wonder if it has to do with the RCFG. Because yeah, let's look at digraph and see if it can return like error undef. This is not talking about any of that. So we were explicitly saying cyclic here. There's a question in my mind. what we could do here is see if we can I haven't tried the debugger on anything Erlang or Gleam. The Z debugger. I don't know that it works with it, and I'd have to Google that. We may do that anyway, but the other thing is now we should remove the top sort function. Oh. There's the problem. A typo. Still, let's go ahead and remove the top sort function. We don't need it. It was trying to call a module which doesn't exist. That would explain the undef. Okay. Let's try to build again. Honestly, that feels like that should be a... Maybe it can't know. That'd be a good thing to add to the compiler. Okay, so now we have actual failures instead of undef. Improvement, I guess. Okay. So we have some things to fix. Let's focus on the uncover live test first, because I think that that's important. Important for us to think through. In that if we have a simple program, honestly it should come out with the same, because there's no Okay, what we were doing was saying this is what how we think the output should be. Let's see, that's figure 35 test. Yeah, that's figure 35 test. That's the first one. What is this business? Did we implement? No? Oh, that's our other graph. It's this one. Honestly, I'm kind of not happy with this, and I feel like we should... It's nice for the printability of it, but I feel like we should do some FFI there, because this library is messy. Right, if you remember when we did chapter 3, we pulled this library in and basically removed a bunch of stuff that we're not using, but I feel like we could use digraph instead, and things might be a bit better. This is the interference graph. but it's just populated with it's hard to read, but it's populated with the base registers. So that might be something that we can do today if we have time. What I want to figure out is ignoring the graph bits. Here, let's close all and just get the uncover live test. So what we should see is that in our Uncover Live algorithm here, what we should see is that we'll start from this as the after set for so like this should be start, like a list containing start, and then we'll create a dictionary with start, and we're giving the list with the REX RSP, right? Because that's the things that are live at the end of the program. And that's probably not the right way to do this. Maybe we should when we build the CFG, create a fake node in there that is conclusion that has no, excuse me, it has no instructions in it. And we seed its mapping with this, and everything else we seed it with the empty list. Something to think about. The reason why I'm suggesting that is that we're starting with this, like, so we have start. It's the only thing in this dictionary, in the mapping dictionary. It's the only thing in the work list. So we're going to do one iteration. We're going to get, this is start, the end neighbors are going to be empty, right? Which means its input is going to be empty. So we're actually going to get the empty set here. And maybe what we do is, the thing is, I don't think it's general to say that REX and RSP are, I mean, definitely RSP. REX might not be live. But RSP we never touch unless we're pushing onto the stack, right? Pushing or popping from the stack. And we shouldn't honestly be pushing or popping from the stack in any of these blocks. Because what we will have done in the prelude is pre-allocate the number of stack locations that we need by pushing. And then all the locations that get assigned stacks are just derefs into that space that we allocated on the stack. So yeah, I feel like we should build CFG. Should add arrows to conclusion. And then, yeah, I think that's what we should do. Because we need the conclusion to have a live before set, which is that RAX and RSP. I think that even feels a little bit better from a completeness. The issue is we need so this means we're going to have no set in there. And then we're going to insert conclusion. Right, because if we jump to that, oops. Here, let me back this out a little bit. What we want is this is the value for conclusion. That way, when we're getting the in neighbors, this becomes, for anything that jumps to conclusion, this becomes the before set of conclusion. I think this feels like the more principled way to do this. It feels a little bit janky. It's just that like we are expecting rather than there being one block or a branching but basically unidirectional, like acyclic flow here. We're doing this iterative we're doing this iterative flow where we're building it up. Now the main problem is potentially, note that if we have this changed, it says we need to add the out neighbors from this node. So if you think of like, originally our graph has, and we could flip it, but our graph has arrows going from the destination of a jump to the current block. So if we have something jumping to conclusion, then we're going to have an arrow from an edge from conclusion to that block. So conclusion is an in neighbor. Yeah, actually I don't think that this is a problem, because we use out. This will be in the in neighbors. Conclusion will never be in an out neighbor. So we should never get conclusion put in the work list. Which is good, because we haven't generated it yet. Now, the only other issue is that we need to ignore conclusion up here. So let's delete conclusion. Because we haven't generated it yet, right? So it doesn't need to be part of any of the I'm sorry, not the liveness analysis, but the interference graph, right? We haven't generated it yet. We don't need to allocate any registers for it. So when we're done, I mean, we could do it in here. That might actually make more sense. Let's do it inside Analyze Data Flow, because that was I don't like that. Let's get. It's okay. I was gonna say let's, you know, my Elixir brain is saying pull out the first argument into the pipeline. Whatever. We're just making sure that we don't have conclusion, because we insert it explicitly here, deleting it at the end. It's sort of like a wrapping it up sort of thing. Deleting it at the end is the right thing to do. So this makes more sense to me. Let's see if we build. Okay. Yeah, I don't care about those warnings right now. Let's run the test. Okay, so now they pass, but we've got a problem with one pattern match and allocate registers. So let's look at that test. That's really good that we got down to one failure. That means that the assumptions we made before about this data flow analysis still hold in the simple cases, and we just need to deal with the more complicated cases. That's really good. Okay, so it's happening on line 72 here. So we got an empty list. So I think that what we need to do here, yeah, and which makes sense because we haven't computed that yet, right? Like we're working on a we're working on an assumption that there is one. So what we should do is we'll call this live sets, and then we'll do if it's empty, we'll just do set new, right? If there's a before ... then we return that. We could do this with like list.first of live sets, which returns a result. And do lazy, or we could do, what is it? Not lazy unwrap. Try, we don't need try, we just want the first. Returning default, that we'll just do set, yeah, so we'll do set new. That's what we want, right? So again, I'm gonna fix my pipeline there so it makes more sense. And we'll get rid of this. Okay. This let assert is fine. That's just saying I mean, there is an implicit assertion here that we shouldn't be jumping to blocks that don't exist, right? So there should never be an inbound edge that doesn't have a source on it. So, yeah. Good. Okay. So I feel like our logic is sound for the cases that we've already covered. So, whew, that was an achievement. We found some interesting problems. Let's go look at. So this one is about branching. That's interesting. Boolean variables. Maybe we should come up with an example of what we want to see, right? The main thing I want to think about here is the stuff that's generated in loops. So if you recall, getting down here, where is that little diagram? It's about explicate control. It's this stuff, right? So when we have a while loop, we have a block which is, go to loop. And then the head of the loop is test the condition. It's basically like compiling like an if, right? If the condition does not hold, then we go to the statement after the while. If it does hold, then we go into the body, we do some things with some mutability, and then we go back to the top of the loop. So we have a bunch of labels here. So there's this fresh label for this, which is that. We have a label for the body of the loop, and then we jump to the continuation, whatever that is. We may create a block for that. So I think I want to look at what we did in explicate control, and I want to say down here we made use of our parser. Yeah. So let's look at this. So we could take advantage of this and think about let's use this example. Okay, and it's gonna be a bit messier. I think we didn't even test select instructions because we didn't need to add anything. Oh, well, there's that. Okay, so we did read statements. That makes sense because we wanted to make sure that things get come out in the correct order. And void gets turned into 0. I don't think that we had. Yeah, we just had branching. We didn't add a while, which is fine. But let's go into. Let's go back to here. And because what we want to do is have something circular, right? So why don't I copy this business, and we will go into our uncover live test. And what were we naming these things? Uncover live something? Okay. Uncover live while loop test. Okay, so we're gonna copy. So here, let me paste this in there. we're going to copy this. We might make a test utility at some point that would be useful. We'll go to the top and get our parser. Yep. Oh, that's interesting. We did that pass twice. I suppose it's fine. Let's get that import up here. Okay, and then the problem becomes making sure we import all of these things. So I kind of want to put, yeah, this is, let's get the pipeline going here. So we have explicate control, import that, import that, import that, import that. Let's make sure we're doing the correct order of passes here. So shrink, uniqueify, uncover get, remove complex operands, explicate control. We need to select instructions. And then here's where we needed to do. Okay, so we're going to say import L while as L. That'll solve that particular problem. Okay, so now we have the intermediate language that looks like assembly. So we have x86 var if, because we've compiled out the while loops at a higher level. So what we want is probably going to be something like this. Let's not... Right, we need to look at the lib before, basically. So let's kind of think through this. And what we should do is look at our explicate control. Come on, split right, please. Okay. So we can look at what these blocks are. And kind of come up with a plan for what we think it's going to be. This is not real pretty. I actually kind of wish it were in assembly. Let's do IO. What I would love to know is how Glee unit does its pretty printing. I don't know the answer to that. Let's see. Oh, it's string inspect. Okay, so we could do let's make a debug function. Okay, now it's just complaining it's not used. So what I want to see here is what the output of this is. Okay, fine. Okay, so we have an x86 program. Wish there were another, like, prettier pretty printing. String. The other thing that we could do is just copy this and like put it in a buffer and format it. Yeah. Okay. So block 1 has no live before, because that's the end. So that makes sense. Okay, we haven't actually computed anything here. This is just the output of select instructions. Okay, and then let's comment this out so that we can just look at it, and we'll do some liveness analysis ourselves. Okay, and that's just the empty graph. Well, it's not empty, it's got all the registers in it. That's a really verbose format of a graph. I really should switch that to digraph. It's okay. All right, so what are we going to see here? I think that we can close that up now. So we've got block 1. This is the end. So I think that it's let's say let P2, let's go ahead and assign this back to P, is going to be uncover live of P. Okay. So in this other test, we did stuff like, yeah, did like this sort of thing. Okay, so we think start I think it's reasonable to assume it's live before is because, I'm sorry, not start. Block 1 is the end. So what's the rule? The rule is that your before set is subtract the locations you write to and union with the locations you read from. So in the case of block 1, it's the terminus of this. It's going to be writing to RAX and reading from some variable sum1, right? So and here, like, this is going to be seeded with its live after set is going to be seeded with RAX RSP, right? So you're going to have RSP is going to be live still, and you're going to have location var of sum.1. I think that's pretty reasonable to assume. Okay. So the other one that should be easy to do, relatively speaking, is start. So I think that we can assume, because we're using some and I in the loop, that that those are live after, right? So the live after for start is going to be some dot one, I dot two, and RSP. Does that make sense? All right, let's copy this. Oops. I just wanted to use the duplicate. There we go. Okay, so we're going to get start. So we know that RSP, we know that I is used inside the loop, you know, because we're setting it. So I think that's a pretty reasonable assumption for start. So now let's work our way backwards into both the loop and block 2 and figure some stuff out. I don't know that we need to go through the entire thing. So we know block 2 is the body of the loop, and we have loop 1. Let's see, loop 1. Okay, it's just the lines are getting long, and so it indented them. Okay, so loop 1, I think it's live before. It has to have I2 and some 1, right? So I think it's live before is that. Yeah, let's so assuming that this this can jump from this can jump to block 1, which is the end of the program, right? So block 1 has someone in RSP in its live before set, which makes sense because we read from someone, and RSP is just in it from conclusion, and because we removed REX from by writing to it. Okay, now so that's one input, is someone RSP. So we know it has to be at least someone at RSP. If we work our way backwards through this loop, that's from block 1. From block 2, we'll get to it. Okay, so then we are here, we're reading from temp 1, so temp 1 is live here. We're writing to it here. We're reading from I2. So the before set also includes I2. So I think that we're fine on that for loop 1. The main thing there being that read implies that it needs to be in the set. So I feel pretty confident about this. So let's look at block 2. So block 2 only jumps to loop 1. So its live after set is someone I2 RSP. So we write to I2, so that's no longer live, except it is. Remember, these things are additive, so even if we are writing to I2 here, that doesn't make it go away. It's just there's going to be... Oh, hold on. So, like, at this point, it's considering not live. We've written to it again, so subtracting temp4 is in the reads, so that's live. So there's kind of this like vacillating bit where in these individual instructions, things are appearing and disappearing, which is kind of weird. And I'm not sure if that's going to be correct, but we'll find out. Okay, let me go ahead and annotate it. So here we have, we're going to have some, because we're coming from loop 1, right? We're going to have some dot 1, I dot 2, and RSP. And then here we're writing to I dot 2, so that goes away. RSP. Here we are reading from temp dot 4. And we're writing to I2 again. So I2 is not live. We removed, not live before. Okay, so we're reading from I.2 here, and we're writing to temp.4. So this is kind of interesting, it flapping back and forth, but now it kind of makes sense that that we have we had to move it to a temporary variable, I guess. Okay, so here we're writing to sum.1 and we're reading from temp.3. So we have I.2, temp3, and RSP. We are writing to sum.1 again. We're reading from temp.2. So temp.3 and RSP. Okay, and then we're moving I.2 into temp.3. So we're reading I.2, it's live again, temp.3 goes away, temp.2, RSP, and then we're reading from sum.1, so that becomes live again. I.2 is already live. We're writing to temp.2, so it's removed, RSP. So like, we have some crazy business going on here. And also you may see that we have like a move into the thing followed by an add. And so these are actually kind of aliased, and we could, you know, we also have a move into the thing and then a move back into the original thing. So we could like possibly squash those as an optimization, but we're not really concerned about optimizing right now. We're only concerned about correctness. So I think that even though these sets look really funky on the inside of a block, what you'll see is that they're same at the beginning and at the end. So so I think that this is reasonable to say we're going to expect the same set for loop 1 and for block 2. Right? Okay. Let's run this test. Okay, so we got a slight failure here. What line is that? The problem is we don't know which one. because a bunch of these have the same thing. So we got an issue with, we only have RSP. Well, unfortunately, we're going to have to comment them out. It's one of these three. So let's go with start. Let's do start first and see if that's correct. And then we'll run the other two. Okay, so it is start. Which I guess makes sense because if you look what happens in start, it writes both of these. So they should not be in the set. That is correct. Okay. That was a little tedious doing that analysis ourselves, but let's uncomment that. But that makes sense because RSP is live through the entire thing, and now we have no failures. Cool. So it's a little bit early. We can try to look into patch instructions. We could look at, allocate registers shouldn't have to change because we still, really we're just getting the live sets for build interference to work with. And then allocate registers, patch instructions. I think it might be interesting to see what the output of that is if we don't even really test it. But let's make a commit here. We're going to say chapter 5.8, uncover live, and remove, replace Gleam Erlang with an FFI. Okay, so I'm going to go ahead and push that. We should now be able to restore everything in here. Except that we have uncover get. Needs to be in our pass. So let's make sure that this still generates, and let's see what it prints out. Oh yeah, that crazy program. Okay, so we're still going full through the stack. We're allocating registers. Let's do our test program from down here. What's going on? Oh, it's complaining about that. Yeah, let's just remove that. It's interesting they removed IO debug. I kind of dislike that they did, but I can understand why, I suppose. Okay, so let's use our sample program here. This crazy one. And let's put it in there and have a look. Okay, well we can fix that. It should be using that. Maybe I have a bug in there. Anyway, okay. So you can see here, jump to conclusion, like we expected in block one. And actually, let's go over to our test here. And I'm going to pull the shell over to the right, so we can see it side by side. Okay, so we had someone is put into RDX, and they jump to conclusion. Okay, block two. Look at how little, like Our patch instructions did a good job here. I didn't have to do anything. That's pretty awesome. It's just like, so here's the add, right? The first add. So it assigned RDX to someone, so RCX must be I too, right? So it's saying add RCX to RDX and sub1 from RCX, and then jump to loop. Loop. It removed an unnecessary move. So loop says compare 0, that's this, to RCX, which was I. And then if greater than, jump to block 2, otherwise jump to block 1. And then our main does, you know, the typical prelude conclusion thing, which is push RBP, move RSP to RBP, sub Q8 so that there's alignment, and jump to start. So, and start, so we know that RDX was given to someone, so that's where the 0 comes from in our program, and the 5 going into I, and then jumps into loop. This is great. Honestly, we didn't have to do much. That's really great. And the patch instructions is still working pretty dang well. So, oops, let me move this back over here. If you recall what we were doing, so like if A and B are the same thing, then it's unnecessary. And probably what happened was in the allocate, if we look at this, probably what happened was, given these sets, like I2 and temp3 are not in conflict, so it gave them the same register. And then it found instructions where it's like, hey, you're moving from one register to the same register, that's unnecessary. And then let's see if any of the others would. This is like if you're trying to compare anything with an immediate, then you know you have to move that immediate into RAX and then compare. That is good to panic. And then if we're moving into a deref, and anyway, so like we removed a bunch of unnecessary moves that were generated in earlier passes, which is pretty awesome. And we didn't have to do any extra work there. So I feel pretty good about this. Let's make sure that this, yeah, let's go to look at that test and make sure that, like, is there a reason why we're not using Uniquify? Okay, that's only used here. So I think actually we need to make sure that the order is consistent in all these places. Okay, so shrink, Uniquify, uncover, get. I don't know that we need. I think this is going to mess some things up in here, but this is going to make this fail because they're going to be named differently. Yeah, so like we'll change this to x2.1, y3.2. That's not a big deal to me. I would rather we be consistent. All right. Wrap up chapter 5. Great stuff, and we're still under the wire for my usual time frame for this stream. So very good stuff. I'm happy with the outcome. I feel like we learned a lot, especially in our Uncover Live, realizing that even though conclusion hasn't been generated yet, we had to have that as an input. That is something that really wasn't called out in the text. Now, what we may do is like scroll up here and I'll see, you know, something, and they'll have conclusion with something. No. I don't know. Interestingly, like here they're saying yeah, this block 8 had to have an input from somewhere of RSP and sum, right? Yeah. And that was probably RAX, and RSP was its input from main conclusion. So I don't know that. Let's scan through the text here one more time. Liveness analysis works backwards, starting, yeah, so. Right, so here's the bit that I missed. And we could start with block 8 because we know what is live is at the beginning of the conclusion, only RX and RSP. So what they're implying here, but that it is not shown in the algorithm, is that you need to seed that mapping like we did here, with the conclusion has its live before set as REX and RSP, and then you can pull from that for the other things. And then if there's, you know, if there isn't something, if there isn't a live before set for the block that's incoming, we just leave it empty for now, and we'll just union it and so forth. And I think that this is pretty good. Okay. Well, good stuff. Let me make sure I've pushed. Yeah, I have. All right, so I'll make a decision in the next few days about what to do next time. We could continue, like I said at the beginning of the stream, we could continue and go into chapter 6, which is about tuples and garbage collection, tuples being fixed length collections, fixed size collections. And then we could go into that. Garbage collection is a super interesting topic. The other thing that we could do is we could think about doing our compiler explorer, which would, you know, generate the assembly in a web page, and, you know, maybe sort of live as you type. That could be interesting just as a fun side project to do some more Gleam in a different circumstance. It'll also give us the opportunity to write, like I've mentioned multiple times, write some JavaScript FFI for this stuff. That would be pretty cool. Otherwise, you know, we can go back and do challenges. We could do the challenge from chapter 4 about removing unnecessary blocks and so forth. So I'm going to give that some thought, and then we'll see what happens next week. So thank you for attending, and I'll see you next time.